Thank you to the organizers for giving me a chance to speak here. For those of you who know me, this might be seem like a strange topic for me to be talking about. So that's actually part of the reason I'm here, which is to learn about what's going on in the field of eruptive young stars. So I'm going to talk for the majority of my talk about some of the work I've been doing on understanding what's the cause or what's underlying the submillimeter variability that we're seeing towards this protostar HOPS 358. And like I said, I'm going to talk about the observational side of this for the bulk of the talk. At the last few minutes, I'll probably try to, if I have some time, try to speculate about what might be going on. But like I said, I'm here to learn. So I've been really excited to hear all of the things that have been going on. And if I say something horrifically incorrect at the end, then that's why we have you all here to tell me what I'm wrong about. We've talked a lot thus far about infrared variability, and our pun beat me a little bit to this. But it's actually kind of refreshing. This is the first time I think I've been to a conference in a long time where HL tau, I was going to say where HL tau hasn't been shown, but I was wrong because I think somebody yesterday showed the streamer going into HL tau, and so alas. But nonetheless, we've talked a lot about variability in the infrared thus far, and this is of course the case of HOPS 383, where in the early 2000s you maybe saw it a little bit in the near infrared. But sometime between, I think, 2004 and 2008, there was some sort of outbursting event that happened, and you see a brightness increase by several orders of magnitude in the near infrared. But this is, of course, challenging to do as you go to younger and younger sources, because as you go to younger and younger sources, they tend to be embedded in these deep, thick envelopes of dust. And so that makes it really challenging to detect them in the near infrared because they are very heavily obscured. And so this is an idea that Doug Johnstone then had, I guess about a decade ago or so, is how can you look for variability in some of the youngest and earliest protostars? And the idea was that if you have your protostar sitting in this dense cloud of dust and gas, and some sort of outburst happens, then the star gets brighter, and then that light should then propagate outwards and heat up the surrounding material, and you end up with a warmer envelope of material, which then, if you go out with your favorite submillimeter telescope, because the temperature has gone up, you should see some sort of brightening of the material. And so this was the idea behind the JCMT Transient Survey, was to monitor a bunch of young stars with the JCMT to look for variability that you could see from the envelopes heating up in response to a brightening of the central protostar. And so they were surveying 8 star-forming regions, about 90 protostars, to look for variability, to try and characterize the occurrence rate of this type of variability in some of the youngest protostars out there. So where do I come into this picture? So circa 2019, the JCMT Transient Survey was ongoing and taking data, and they noticed that one of the protostars in their sample, HOPS 358, had gotten to the point where it was dimming, and they got to the point where they said, oh, this is a statistically significant decrease in the brightness. And so this is something that we think is varying. And around the same time, ALMA was taking observations for John Tobin as a part of the Van Dam Orion survey to survey all of the embedded protostars in Orion with ALMA to look primarily for things like multiplicity and disk properties. But it just so happens that about the same time, these observations were at about the same time. And I was working as a postdoc with John at the time, and so Doug got in contact with us and said, hey, we see that HOPS 358 is varying. Do you have any data on the source at the same time? So we took the observations. Fortunately, the ALMA actually took those observations over the course of a few epochs. And so we split those up. We imaged them separately, did a quick estimate of the flux. And sure enough, albeit with quite large error bars, we saw that, hey, maybe something is happening in ALMA as well. So we wrote a DDT proposal that was rejected because it was about a month away from the, I think, cycle 7 deadline. So we proposed again in cycle 7, and we're lucky enough to get a series of ALMA monitoring observations of HOPS 358 to try and look and see whether we could detect changes not only in the brightness of the envelope, but also in the brightness of the disk as well. And so we ended up getting additional 6 observations over the course of about a year and a little bit, I suppose, over the course of from end of 2019 to early 2022. Do I do that wrong? 2 year? Anyway, I'm going to not do mental math. And so we have we got a total of 9 observations of HOPS 358 over this 2016 to 2022 or so time span. And here are the observations that we got. And so you can probably already see that there's a bit of a problem here, which is that because ALMA is constantly changing its configuration, the spatial resolution of our observations changed pretty dramatically over the course of all of these images. And so what we wanted to do to try and make sure we're comparing apples to apples and comparing fluxes in an equivalent way, and I'm going to kind of go through this quickly. Feel free to ask me questions, but I want to make sure I have enough time. We basically tried to match the baselines, match the spatial scales across the 2 observations by picking only baselines in one observation that were close to baselines in another observation, and then of course weighting it properly and such so that you end up with a proper set of spatial frequencies that overlap, not just in having something close to it, but also making sure that the actual weighted distribution with UV in the UV space or with UV distance is similar. And then the end result then is that when you take any 2 observations that we from our sample, that you can image them and get something with a fairly similar spatial resolution. So this is just one example of our 3rd epoch, or I guess 4th because I have 0 indexed here, compared with our 0th, our 1st. And it doesn't show up tremendously well here on this screen, but you can see that, and I'll come back to this in a second, but you can see, albeit with the issue of flux calibration, since these are on the same scale, that there is perhaps a change in the brightness of HOPS 358. We also got really lucky because, like I said, the flux calibration is, of course, a concern here. It's almost good to about 10% or so, but we're looking for fairly small variations, and so you have to be careful here. And so we are fortunate that in there is a source in the same field of view about 13 arc seconds to the south that we can use as a reference, albeit assuming that that source is also not varying at the same time. So we made these images for the visual comparison, but in practice, what we actually do is that match all of our observations to the resolution of the lowest resolution observation that we took, where HOPS 358 was marginally resolved, so we can fit it with, the disk was marginally resolved, I should say, so we can fit it with a Gaussian to measure the flux in a relatively comparable way. And so the end result of what we got looks like this. So in the top left, I'm showing the flux that we measure for HOPS 358 as a function of time. And you can see that there's fairly large error bars. And on the bottom row is that southern companion for comparison. And so you can see there's perhaps some evidence that the flux of HOPS 358 is decreasing with time. But you can also see the effect of the flux calibration uncertainty, because those blue and orange points on the far left were taken about a few days apart and have wildly different fluxes, which I don't think is a real effect. So what we did to try and look at this in a flux calibration independent way is we looked at not the absolute flux, but the ratio of the brightnesses of HOPS 358 to the southern companion, which is what I'm showing here in the top right now. And so now here, since you don't have to worry about the flux calibration, what you can see is that in a very statistically significant way, there is a decrease in the ratio of the brightnesses down to about the middle of the plot, and then it starts to rise again, which, since the JCMT continued to observe this source since our initial proposal, you can see actually, and that's what I'm showing here in these gray points, matches quite nicely with what we see the JCMT observations doing at the same time. It's actually quite remarkably good. So again, you have to make the assumption that that southern source is not varying, which we can perhaps discuss. But if you assume that, then there's some evidence that the HOPS 358 disk is varying in brightness in ALMA as well, and it matches quite nicely with the overall trend that we see from the JCMT. And like I said, the JCMT also continued to observe the source, and after that initial about 20-month decline in brightness, 5 minutes, okay, started to get brighter again. I am going to be very careful to not say that that is periodic, but if you put it, fit a smooth curve to it, then what you see is that there's perhaps these residuals that look like there might be some shorter period ringing on top of the overall smoother trend. And so the JCMT folks did a fit and got a period of about just under 2 years with a 3% amplitude on top of that perhaps longer period trend, which we say is greater than 8 years because we have not yet, well, there is absolutely no evidence at this point that it's going to repeat, but that's about the time scale for this overall variation. Carlos also grabbed some mid-infrared data for us to see, and you can see that it's also varying sort of in the similar pattern. Those are those fit curves again. It doesn't match exactly, but that's just to say that it is in fact varying in the mid-infrared as well. And then you may have noticed this, I've kind of hinted at this or skipped over it, or it's been an Easter egg in some of the slides, but it turns out with the highest resolution observation we got with ALMA had a resolution of about 30 milliarcseconds, and so we could resolve the disk quite nicely and start to understand its structure. And what we actually found is that, and it doesn't show up tremendously well again on this screen, but you can actually see, so I was gonna say you can see quite clearly, maybe you can't quite see it as clearly as I had hoped, that the disk is in fact warped. The disk at about 35 AU, we fit it with a model that tried to just do a simple fit to the intensity profile, and we get that the disk has about a 16-degree warp or so at a radius of 35 AU. So I think that makes this a very interesting source. It's obviously interesting in the fact that it's varying and what's going on there. It's also very young and sort of to the point of this conference in the prime time for forming planets, and it shows the disk warp. So how do all of these things tie together? So this is, like I said, the part where I get a little bit more speculative, perhaps. So bear with me. But we looked to see whether there was any evidence that this disk could be perhaps gravitationally unstable. We have the ALMA observations, so we can get a rough estimate of the mass. And so we tried to do a very simple calculation of Toomre Q, and the short version is that it doesn't seem, it's at least even in the outer regions of the disk, seems like it's at least an order of magnitude too high to necessarily be gravitationally unstable. So maybe we need some sort of other instability in the inner disk, perhaps, to try and account for why this disk might be varying. And then, of course, it's not obvious, even if it was gravitationally unstable or whatever instability might be going on, that this would actually explain the warp in the disk. So to the talk earlier today, one way you could potentially explain that warp is late infall from the cloud, or perhaps the change, the change in the angular momentum vector of the infalling material, which has been shown to create misaligned disks. But of course, it's not necessarily obvious that, as we heard this morning, that would even explain the variability either. And then the other thing that we perhaps I could speculate about is whether there's perhaps some sort of unseen companion hiding in the disk that could explain possibly all of these things at once. The obvious place that came up to me would be to put it at the location of the warp, but in terms of thinking about the variability, the timescale at 35 AU, the Keplerian timescale, is about 200 years, which doesn't match at least some of the timescales, albeit again with the caveat that we haven't even observed any repetition or what the full timeline of the variability is. You could also put have a much closer companion, and there's been some papers showing that you could, perhaps with a misaligned orbit, drive a warp out, further out in the disk, and that could help explain the timescales. Or, as I've said, there is this southern companion that really doesn't show up very well, but you can see this southern companion as a tiny little blob down here, and HOPS 358 up there. So, if you squint very, very hard. There is the southern companion, but it's not necessarily clear that that's actually close enough to have impacted the disk at the current moment. Though perhaps Edward's talk earlier says that it doesn't need to be right next door. So, so overall, I think I'll just leave you there with a summary of a few of the more salient plots from the talk. But hopefully, I've convinced you that this is at least an interesting case of planet formation, of how the timescales for eruptive young stars and planet formation might work together, and that perhaps the submillimeter observations can help to illuminate some of these processes. So, thank you.
Could you switch back to the slide where you had this kind of plot, but with also the NEOWISE data?
There.
Yeah, there we go. Yes, yeah, I had also looked up the NEOWISE data after being alerted to this decline in the HOPS data, but or in the JCMT data. So to see it overlaid like this is really great. Is there any delay, any time shift that went by very quickly, so now we can see it?
Right.
A little more slow paced, in this whole scenario where the submillimeter variability is just the bolometer, and the light bulb at the center, something happens with the accretion, and that's reflected later, some time later in the submillimeter. Do you see an intermediate of the NEOWISE?
My recollection is I don't think you needed to do any, Carlos maybe be able to answer this better, but I don't think we needed to do any shifting to make these line up. I'm seeing Carlos shake his head, so no, it looks like they sort of line up overall in terms of timeline.
Just a brief technical thing, the JCMT is 850 and the ALMA is what wavelength?
ALMA, oh yes, ALMA is also well, so JCMT has 450 and 850, and then ALMA we did at 850. Technically like 875 or something, but.
Hi. Yeah, probably a stupid question, but so you show that in the different epochs, the morphologies and flux are quite different. Then should we be concerned about imaging ALMA data and trusting their morphologies and fluxes?
So the difference that we see, let me see here if I can. The differences that you see here are almost entirely based on the beam, right? The UV coverage changes pretty substantially as the ALMA configuration changes, and then of course where you when to observe it. So yes and no. I would say you need to be very careful, especially if you have a source that is resolved in some of your observations, to be comparing the flux on comparable spatial scales, right? I wouldn't necessarily recommend drawing a box around this, measuring the flux, and drawing a box around this and measuring the flux. It's going to depend on your source morphology, right? But HOPS 358 is young; it has an envelope. You have to be careful about all of that. So, to the extent that you can, it's good to try it. You really want to try to match the spatial scales to make sure you're observing fluxes on the same spatial scales. So you should be concerned if someone just shows you a plot like this and draws a box and says these are the fluxes. If they've done the careful thing of trying to match and whatnot, then you don't have to be quite as concerned. You can be concerned about how well they did that, but at least they've done the effort.
Can I ask another question?
Awesome talk, Patrick. So I guess my question is somewhat related. So in all these epochs, if in some epochs you see the disk is slightly resolved, then you also see variability. Does the entire disk brightens uniformly, or?
Yeah, we don't have enough spatial resolution across most of the epochs to really be able to do that. The short version is I don't know, right? You know, most of our epochs, the disk's not tremendously well resolved. It's really, we'd probably need a bunch more that look like this to be able to say that confidently. I did try to take the, there. I did try to take the results from this modeling and use that as priors on fitting some of the earlier epochs, but it didn't go tremendously far and it wasn't working very well. So something to think about. I don't know if the data are good enough to really say much about that.
Sorry if I missed this, but did you check if the flux variation is consistent with maybe an m dot variation that you could assume from the WISE light curve changing, driving the heating? So you get, you know, m dot moves up and down, heats the disk differently, and then that'll give you some flux difference in the millimeter. Did you check if those are consistent?
So if I remember right off to think on this, I believe so the millimeter variation roughly then goes like, I think, brightness to, or the change in the luminosity goes like the brightness to the fourth or so, and that was about consistent with the magnitude change that we saw from the NeoWise data. That's sort of the extent to which we compared that.
Thanks.
That is all we have time for. Let's thank Patrick and all the speakers. All right, I believe it's lunchtime. Thank you for being present and paying attention. Go get some food. We do have